All right, so persistent memory in Linux. The end goal is really to talk about how you get started using persistent memory. The code is out there, it's in the upstream kernel. But to really get you started with it, I kind of want to tell you what the status is, so what works and what doesn't. And in order for you to understand that, I really have to start with the overall architecture. So we'll get started there. I'm not sure if this slide got shown yet today, which really surprised me. This is like the most popular slide for at least the Twig members ever. It's the squiggly red line slide. And down in the bottom left squiggly red line, that's the interface between NVM drivers and the operating system. So any file system interfaces or device driver, stacking device drivers might want to use the functions defined there. The upper right one is the more interesting one for today's talk, and that's how applications make use of persistent memory. And it breaks down pretty much like this. And this is a slide that I kind of stole from Intel. I mean, I remade it, but you have a persistent memory aware file system, and that simply means it's able to hand out these mappings. And you have an application that will then call into that file system to open a file descriptor. And I think Neil did a good job of explaining why the file system is involved at all. And that was a core piece of the programming model, was to reuse all of the benefits that you get from the existing file system model. So step 2 then would be simply M-mapping it, and that causes this translation to be installed for the application to directly access the NVDIM. Step 3, you can do whatever you want with it. You now have direct load store access to the media. And of course, step 4 is to profit from it. So that's possible. That's a very simplified view of what's going on under the hood. This is the stack. And I think I'm on a short tether. But in the bottom left-hand side, we start with the ACPI NFIT. And that is the NVDIM firmware interface table. It describes NVDIMs, how you get access to them, what the memory ranges are, interleave sets, all the things the driver knows to expose this to the operating, or needs to know to expose it to the operating system. On top of that, you have this NFIT core, which parses all of that. And tightly coupled to that are these drivers, the block window driver, the persistent memory block driver. Layered on top of them is this BTT that you just heard about. It's listed there as optional, but for legacy applications, I pretty much view this as mandatory, at least the way Linux deals with this. You really don't want to do raw persistent memory accesses through the block stack without the BTT, otherwise you're introducing new failure modes. On the far left, you have the management tool chain. That would be libraries and utilities on top of it. You have traditional file systems layered on top of the BTT in the center. To the right, you have a DAX-enabled file system. How's that? Good? All right. So you have the DAX-enabled file system, and that's what we saw earlier, setting up these MMU mappings for the use of the persistent memory programming API. And then, of course, in user space, you have some libraries for dealing with abstracting away all of the intricacies of accessing NVM. So the programming model defines actions for files, nvm.pm. PM stands for persistent memory.file. A couple of those are implemented by the kernel itself, and a couple of those are up in user space. As we saw, there's map, which allows an application to get a direct access to, load store access to a piece of persistent memory. Sync is also implemented by the kernel. It is sort of like, well, it is implemented via msync in Linux. And there are some reasons why you wouldn't want to use that, mainly because context switches into the kernel are expensive. And the granularity is also much different from, it's a page size granularity as opposed to a byte granularity that you might want to use for your program. And so because of that, there are these two other instructions or actions. There's optimized flush, which is just a way to flush caches from user space applications. And there's optimized flush and verify, which is meant to provide the equivalent of a POSIX synchronized I/O support. So if you have one of these DAX PM-aware file systems, and you wanted to do reads and writes to them, what would that look like? Today and going forward, it bypasses the page cache, much like Windows does. So it ends up looking a lot like the direct I/O code path in the Linux kernel, if you're familiar with that. And it's also synchronous, and it's synchronous in a couple of ways. The first way is that because it's persistent memory, there's no HBA involved, there's no interrupts. It's really just a mem copy. So once you return from a read or a write, the data transfer is done in the submission path. So there's no context switching or sleeping of the process waiting for an I/O to complete. But the other way it's synchronous is that because of architectural limitations in the kernel, any kind of flushing that has to happen for CPU caches is done before you even return to user space. So that's kind of expensive and maybe not ideal, because one programming model would be to issue a bunch of writes and then later fsync or msync when you're ready to do ensure all your data is on disk. But we don't keep track of all that data. Disk caches are easy to flush. You just send a command. You don't have to know which ranges you touched beforehand. You just send that flush down, and you know that as long as you've waited for all of your IOs to complete, that has now flushed all of the cache. The CPU has an instruction to do that, but it's really expensive and would be really mean to every other application on the system. So even though it's synchronous, which sounds really safe, it isn't. It still suffers from torn writes, as explained earlier. So you have to be really careful when using reads and writes to a persistent memory-aware file system that's not running with a BTT under it, essentially. So for error handling, there's a couple of cases to handle. There's the case where an application happens to trip over a poisoned area in memory. And so you didn't know beforehand that there was poison there. And then there is some means to keep track of known bad blocks and do something clever about that. So I'll start with machine checks. The goal is to make this API look as close to something you would get from a real disk storage system. So, or in this case, in terms of like if you were using DRAM with memory mapped files, if you got a machine check, you would then get a SIG bus. We want the same thing to happen for persistent memory. Problem is right now in the kernel, I believe machine checks will kill the process that's running. So there are patches in flight that will change this to handle it properly. And turning it into a SIG bus is great, except that not all platforms will allow you to handle this gracefully. And even on platforms that do allow graceful recovery from machine checks, there are cases where the processor context is corrupt and it can't continue anyway. So because of that, if you imagine your file system metadata has a poison region, you boot, you trip over this poison, and so you reboot, and so you trip over this poison, you reboot. You have to have a way to break out of this endless reboot loop, and that's where this known bad blocks comes in. Essentially, the platform firmware, like UEFI, is expected to initiate an address range scrub when the system starts up. And then after the kernel's loaded, the driver subsystem will query the status of the address range scrub. And it'll gather a list of all of the bad blocks that were found. The address range scrub just walks over all of persistent memory looking for errors. So you store all of these addresses into a bad blocks list. And the bad blocks list is stored per block device. And the implication there is that the granularity of errors for the Linux kernel for persistent memory is not byte or cache line or word size, what have you. It's actually per block as defined by whatever block size is set for your PMEM device. So 512 bytes is the finest granularity you'll get for errors. That means that if you only had, say, 128 bytes failed, you're still going to lose the rest of that 512 byte block. There's no way to recover that application data. So that's important for application writers to know when designing their applications. So having gone through that, I'll talk about the status. And I put this slide up because it's not just writing a device driver. This isn't an easy hardware to add support for. This touches everything. You have, as I mentioned, parsing of ACPI tables. You have device drivers that are built around this to set up a whole new bus driver and other drivers that plug into that. You have architecture-specific code for machine check handling. You have block layer changes. You have virtual file system changes. And then the file systems themselves need to change to become persistent memory aware. And then the memory management subsystem, which is by and far the easiest subsystem to get changes into. So in addition to the kernel, which I focused on here, there's a bunch of user space components that also need to change. The most interesting is virtualization. So QEMU has grown support for persistent memory. You can actually set up a system and get persistent memory without actual persistent memory in the box. So that's a good testing framework that's released in QEMU 2.6. But I don't know if they've released 2.6 yet. It's destined for 2.6. Libraries, obviously. NVML and libndctl. NVML we've heard about. NDCTL is a management library. kexec required changes just to support new memory types. Pretty simple. The installer needs to know how to install to this media, but also how to not fall on its face when confronted with it as well. SmartMon tools, when some DIMMs will report smart data, and since SmartMon tools is where applications look for this data, that needs to be extended to support it. And then management utilities built on top of that libndctl are also required. So moving on to what works. The NVDIMM driver core is there. It detects, parses the NFIT, sets up devices for you. That all works just fine. The drivers I mentioned here, the PMEM driver creates the block device for the persistent memory. So when you boot your system, that's what you'll be accessing. But there's also the BTT driver, which can layer on top of that. An ND block layers on top of a different mode of access to NVDIMMs. There's a windowed mode of access where the address space of the DIMM isn't mapped into the system address space. It's actually accessed via block windows. There are advantages to that. One is that you don't have to worry about stray pointer accesses corrupting your actual storage, which is beneficial. The DAX support is in the kernel. It's been in there since 4.0. However, that was before the driver subsystem was even in there, so it wasn't too helpful. But now with the NVDIMM driver core in, you can play around with DAX. I list 4K and 2 megabyte pages here because you can map files with 4K or 2 megabyte pages as long as they're aligned properly. The 2 megabyte pages is obviously to help reduce TLB pressure. The two file systems that we're going to support that have been modified for use with direct access are ext4 and XFS. The support, however, is preliminary. They're both marked experimental. The bad block tracking infrastructure is in place, but if it finds bad blocks, it will disable DAX on your volume. So That's not fully baked. And then core dump filtering, in case you don't want to dump all of your storage when your application dumps core, you can turn that off. It's actually off by default. So what's missing? I mentioned DAX has some issues. There's fsync and msync support. The patches have been posted, but they're not in the kernel today. I think they're probably going to go in for 4.5. 1 gig page support, and I mentioned 512. I've mentioned 4K and 2 meg page sizes. There is also interest in supporting 1 gig huge pages for mapping persistent memory, since it could be quite large. But that support isn't in yet. There are patches posted, but file systems still aren't allocating 1 gigabyte aligned and sized chunks of data to even map. So there's still work to be done there. Error handling, I mentioned the machine check code. That work is underway. It's looking in good shape, but I don't know which release that will hit. And then management utilities. Right now there's the libndctl. There's an ndctl application that goes along with that, but it's very rudimentary. So we expect other management utilities to spring out from there. So, getting started with persistent memory. There's a few things that you need to do. There's I'll go through the kernel config options, how you create and mount a file system, and then how you would actually write an application to make use of it. So here's the laundry list of config options that have to be enabled. And in order to do that, it's kind of a pain, because you have to disable config zone DMA for old sound cards. That's basically all that uses them. And then in order to do that, you have to set up config expert, and that will ask you 100 other questions. So the bottom line is just use the Fedora kernel, because it's really, I mean, it took me like 45 minutes to figure out how to get it enabled. It was not fun. It's probably going to take you a little longer than that. Anyway, so Fedora has most of these options enabled today, and I've been talking with the Fedora kernel maintainers. We'll have all of the options. What's missing now is the config zone device stuff, which allows DMA to and from persistent memory, which I guess I didn't mention as one of the shortcomings. Right now, DMA to and from persistent memory doesn't work. I think that one is going into 4.5. Martin, do you know?
I don't remember.
Okay. So the next step after you've gotten a Fedora kernel is to, if you don't have persistent memory in your box, I mentioned that you can use QEMU to emulate persistent memory. But you can do it on bare metal as well. You can just pass this kernel parameter, memmap equals 16 gigs, bang, 16 gigs. And that would put a 16 gig section of persistent memory at a 16 gig offset into your DRAM. And so instead of all of that memory showing up to the kernel as usable memory, 16 gigs of it will be reserved for the persistent memory drivers to claim. And then you'll see on the right here, I just do an lsif/dev, and you see the pmem0 device there. And you can run fdisk on it or any other disk utilities to see the size. You can partition it if you want. And then the next thing is making and mounting file systems. XFS has options for passing RAID geometries to makeFS. And when you do that, it actually tries to align data on the boundaries that you give it for more performant I/O. It avoids things like read, modify, write on, file system block sizes. So if you pass those, I just used 1 gig as an example here. You just pass those options to makeFS, and then you can mount it using this -o DAX. And then the ext4 instructions are below, very simple. DAX stands for direct access. It was born out of zip, which was execute in place. I think the X is for cool factor. So there are inconsistencies in the behavior of mount, which drives me nuts. So I'm working on trying to get some consensus there. But right now, if for whatever reason there's any parameter that the file system doesn't like, ext4 will just fail the mount command. but XFS will happily mount the file system, but you don't have DAC support. So you have to check dmessage just to make sure you got what you thought you got. And then for using it, this is just like my first few slides. You just open the file name and then go ahead and mmap it, right? It's that simple. Except maybe you want to make sure, as an application programmer, you don't know who mounted the file system or they actually have DAC. So maybe you want to make sure that you actually have a persistent memory mapped. And so you can look in proc self smaps. And there's a VM flag called MM, and that stands for mixed map. This is the worst interface ever, but but that's what we have, and that's the only way you can check to see is if you got persistent memory, is to walk this, look for the memory range where the address is that you got, and then check for this VM flag. So it's very simple. You just do this, followed by that, and then a little bit of this. Or you could use NVML, which has a single function called pmem is pmem, and you're done. So, and that's kind of where I borrowed this code from. Yeah. So the summary is BTT is for legacy applications, and you really should be using it. It kind of is not ideal that you have to separate legacy applications from new persistent memory applications like this, but I really think that the torn sectors problem is big enough that you really do want to try to do that. Persistent memory devices, the PMEM devices, you can use them directly for the modified applications. Today you can get started using nvm.pm.file.map, and sync is coming very shortly. How am I doing on time?
It says summary, so I'm assuming you're near the end.
I am. Do we have time for questions?
Yeah, a few questions. That'd be great.
Go ahead.
Well, you indicated writes are synchronous, so then wouldn't fsync and msync just be no ops at that point? And what exactly is going into 4 or 5 that needs to be fixed for it?
Right. So with writes, reads and writes, not mmap. And if you wanted to do reads and writes in fsync, let me talk to you afterwards because it's going to be a string of conditionals. Go ahead.
You mentioned that you have to build this bad block table in the scrubbing process. How often does that occur, and how long does it take?
How long the question is the bad blocks list, how often do you create it or call the address range scrub routine, and how long does that take? How long it takes is going to be dependent on the media. It will vary from vendor to vendor. How often you do it is, it's definitely going to be run every system boot. There is an administrative command. There's a device-specific method that you can run to also initiate it during runtime. But you don't have to. You could just trip over machine checks.
But ballpark, how long would it take when it gets in?
I can't give you any numbers. I'm sorry. Any other questions, Steve?
Yeah, I just happened to wonder whether ext4 uses a BTT trick for handling torn writes, or whether it's got some other option.
The question is, how does ext4 handle torn writes?
Yeah.
Their log has never assumed that torn writes cannot happen. So their logging code is written in such a way where they will detect torn writes. XFS actually didn't require much change to support this either. Initially it didn't, and then it was mainly just the head and tail pointers for their log needed to be checked more carefully, if you will. Yeah. Yes?
I'm just wondering if a bad NVM media will always show up as the same physical address when you put it through the OSM.
I'm not sure I understand the question.
Well, in a lot of these NVM technologies, they have some kind of remapping that goes on inside the DIM.
Okay, so if there is a bad section on the DIM,
Right.
then that absolutely has to be surfaced to the operating system so that an application can understand that its data is gone, right?
Yeah, I guess.
It's the infid that's controlling where that stuff goes.
Okay.
And it's the bring up bias that'll control where those bad blocks are. And it can do the translation so you get the same, you'll get the correct address no matter what it does.
So,
Oh, one more.
One more?
Thank you. Maybe I should ask Neil same question as well. I understand you guys sort of intended play it a little bit lightly. And we also understand there are a lot of things we need to do, right, to make this whole thing work. So what's the next step? We see there are other holes still there in the system. So what's the next step? Roadmap thing? Like, what do you want
For the operating system or for applications?
from your application viewpoint? What do you
For-
want next? In a few months, for example.
I would hand that off to someone who's working on NVM libraries. The two big things I think are most interesting right now are management and application libraries for support. I would say and when talking about applications, I would say Java support would be the #1 thing on my list, is surfacing APIs so that middleware can make use of them. Because basically, when you look at the problem space, if you can update middleware and database transaction managers, then you're modifying very small pieces that affect a lot of the other applications using them.
Jeff, thank you very much.
Keep.
So, I'd like to point out when we started the NVM programming twig, it was a very conscious decision, I know Andy was part of this, was to stop short of APIs. And there was many reasons for that. One was that, even if we tried to do APIs, by definition across operating systems are going to end up different anyway. And it just kind of dawned on me that, here we had a Microsoft speaker and a Red Hat speaker come up, and there was more similarities in what they said than differences. And I think that was absolutely the intention here. It's sort of, can the programming model focus us in on having the common features across multiple operating environments? And I think these two talks validate that, at least from my perspective, validates that there was a success in that regard. So just an observation on my part there. So there is a break time, but if we don't take a break, we are absolutely on schedule. And I'd like to keep us on schedule. There is food out there, so what we're...
I do think we do. For our demo people, I think we do.
So we discussed this already,